Continue our discussion, but first let me just recall a few things. I know sometimes these concepts seem to be quite convoluted. That's why we have to keep things in mind. So we're dealing with the Minkowski space, and we're dealing with a set of transformations in Minkowski space which preserve the norms of vectors in the Minkowski space. And the norm is defined according to a certain metric, which is the Minkowski metric. And such a set of transformations forms a group called a Lorentz group. And the very property of preservation of length demands that the determinant of those transformations must be either equal to +1 or -1. And furthermore, there's one particular element, the lambda 0, 0, that has to be either larger than or equal to 1 or smaller than or equal to 1. And thus, the Lorentz group L4 can be separated into 4 parts. First is called the proper orthochronous. This means that the determinant is +1, and the lambda 0, 0 is larger than or equal to +1. And then we have the lambda minus, how these 4, put them in a particular order. Well, it doesn't matter how, what kind of order you put them in. This is the lambda minus up, determinant -1, lambda 0, 0 bigger than or equal to 1, and then L minus down. This is determinant equal to -1 and lambda 0, 0 less than or equal to -1. And finally, that's lambda plus down, means determinant equal to +1 and lambda 0, 0 less than or equal to -1. The whole thing is called L4, the Lorentz group. And in this first one, sometimes has a couple other names to it. Actually, the whole thing is also called O13. O kind of sort of generalization of the orthogonal groups in ordinary rotations. This 1,3 means that one of the dimensions, in this case time, has a metric element which is different in sign from the other 3. The time is treated separately than the spatial ones, okay? And so this separates into these 4 pieces. This one is also sometimes called SO13 up, and also sometimes called L sub 0. This one is called a proper orthochronous group, which is actually a subgroup of the Lorentz group itself, because the identity clearly is in there, okay? None of these others are groups, although they are pieces of the whole thing. These are not subgroups simply by virtue of the fact that none of those contain the identity element, okay? And you can write this, you can treat this as being equal to, since the determinant is -1, it involves either a spatial inversion or time inversion. So this one can be formed out of multiplying the things in L sub 0 by the spatial inversion, which is flipping the signs of all the spatial components. So -1, -1, -1, 1. Now this one can be written as time inversion multiplied by L sub 0. But the time inversion is actually the same as the metric element, a metric tensor rather, 1, 1, 1, 0, 0. Okay, so it only flips the time coordinate. The spatial ones are not flipped. This one is ST L sub 0. Okay, so keep in mind this basic situation in here. We can show in one of the exercises, we show that not only is this a subgroup, but a normal subgroup of L4. And so therefore, we can take the quotient group, O13 divided by SO13. Okay. This splits up the whole thing into cosets. And the cosets are precisely these four things in here. Okay. So that in this quotient group has 4 elements in it. Okay, and you can figure out the multiplication rule and so on and so forth. And this is one of the exercises that we have seen. Okay. So we write this as SO13 up itself, and then L minus up, L minus down, and then finally L plus down. Okay. So this quotient group consists of 4 elements. All right. With this one being the identity, of course. Okay. And then we can imagine using the definition of multiplication of cosets, in a former chapter, then we can see how these things get multiplied together and so on and so forth. Okay. Now, the next thing we saw was that we introduced this map in here, which maps things in Minkowski space to things in 2x2 Hermitian matrices. This turns out to be an isomorphism. It's a 1-1 and onto relationship. And so this allows us to think of H2 as a linear vector space, a 4-dimensional real vector space also, much as the Minkowski space is a 4-dimensional real vector space. Okay? The mapping is such that f of E sub 0, where E sub 0 is like 1, 0, 0, 0. So this points along the time axis, and we can construct another 3 similarly. This is 0, 1, 0, 0. This is 0, 0, 1, 0. Finally, this is 0, 0, 0, 1. It maps f E sub 0 to something that we call sigma sub 0, which turns out to be the identity matrix, 2x2 identity matrix. And f maps E1 to sigma 1, which is the x component of the Pauli matrix. And f E2 is sigma 2, which is the second Pauli matrix. F E3 is the third Pauli matrix. And the mapping works like this, that f acting on any general vector in Minkowski space takes it to this particular 2x2 Hermitian matrix. X0, is it plus or minus? Plus x3. And then x0 minus x3, x1 minus ix2, x1 plus ix2. You have seen all of that, okay? And then using this prescription in here, then you can basically figure out what the sigma matrices are, which are very important objects in quantum mechanics. And it's worthwhile to remember. This is one of the few results in quantum mechanics, in physics, that worthwhile to kind of keep permanently in your hard disk inside here sometime, okay? So sigma 1, even though I cannot do it, okay, is 0, 1, 1, 0. Sigma 2 is 0 minus I 0. Sigma 3. Sigma 3 is what's called a spin flip. It flips you from spin a half to spin minus a half, so to speak, because of the 1 minus 1 in there, okay? But in any case, the sigmas are the representations of the angular momentum operators on 2-dimensional representations, okay? So it's a representation of SO3, but the representation is 2-dimensional. And so it tells you how to rotate spin vectors in physics, okay? It tells you how to rotate spin vectors in physics. Because the angular momentum operators are basically the infinitesimal generators of rotations. So once you know how to rotate spin vectors infinitesimally using this, then you can do e to the I something and to do a finite rotation, okay, on spin vectors in physics. Mainly the spin vectors are the 2-dimensional vectors that we consider in quantum theory. Okay, so we then have the following picture that there's a map F which maps M to H2, and then we consider the transformations. The L4 are the things which maps M to M, which preserves the length of the vectors. And we are going to define a group homomorphism going from the group SL2C to the Lorentz group, like this. And so let's consider some Lorentz transformation. Let's consider something in this G. Phi of G takes you to something in L4, okay? G is a 2 by 2 special linear matrix with complex entries. This group homomorphism phi maps that G to some 4 by 4 matrix, which is a Lorentz transformation lambda. And so we do something like this. So then F inverse. And so supposing there's a G in here, which takes you, G of course is 2 by 2 matrix, so it takes 2 by 2 Hermitian matrices to 2 by 2 Hermitian matrices in a certain manner. We'll show you how. And this G is inside of SL2C. And this gets mapped by the group homomorphism phi to some phi of G, which lives inside of L4, like this. So it's essential to keep this kind of a diagram in mind. And now the most important statement is the definition of the group homomorphism. This group homomorphism is a mapping between two groups which preserves the multiplication. Okay, and we've proved last time why this is a homomorphism. If we make this definition in here, group homomorphism is defined like this. So given any G, I'm supposed to tell you what the action of that homomorphism is. This is supposed to produce some particular Lorentz transformation for me. In order to specify that Lorentz transformation, I have to tell you how that Lorentz transformation acts on a particular Minkowski vector. Okay? So then I have to tell you the result of this. Well, X is some Minkowski vector. Okay? And that particular Minkowski vector is then the inverse. F is an isomorphism, so we can go back and forth, forward and backwards. F inverse of F inverse takes you from H2 to map, okay? H2 to M. So I have to have something in here which is inside of H2, and the thing which is inside of H2 is supposed to be this. F X G Hermitian conjugate, like that, okay? So given any X, I know how to find Fx, and given a G, I know how to calculate this. We've proved already that this, if Fx is in H2, then this whole thing is in H2 also, and for something in H2, I can use this map to get me back to something in M. Okay, so this equation defines the group homomorphism, and we've proved last time why this is in fact a group homomorphism. Yes?
Do you know who came up with that?
I don't know. Can't tell you for sure who. Possibly Wigner. I don't know for sure because Wigner was the first physicist who worked out in its entirety the representation theory of the Lorentz group. That was in 1939. Before it was realized, I mean, relativity came out in 1905, right? The special theory of relativity, general theory came out in 1915 or so. But before 1939, people were suspecting that, of course, the Lorentz group had to be very, very important in physics, but nobody worked out the details in mathematics behind the representation theory of the Lorentz group until Eugene Wigner did so in 1939. Okay? But still, even though it was worked out in 1939, physicists did not make use of the results until into the 1960s, when it was realized that the various representations of the Lorentz group actually allows you to identify various kinds of particles, elementary particles in all of physics, whether it's a boson, a fermion, this spin or that spin and so on and so forth, okay? But the short answer to your question is I don't know. All right. Okay. So now we found out something about this homomorphism. This homomorphism is 2 to 1 because phi of given any g, so you know phi of g, but we found that phi of g is exactly the same thing as phi of minus g. Okay, for a very simple reason, because the g occurs twice in here. So if you stick in a minus sign to each one of these, you don't make any difference, okay? And so phi of g happens to be 2 to 1, so it's not an isomorphism, okay? And we're going to discover that it's not an onto map either, that the group homomorphism phi only takes SL2C, not to all of L4, but only to the proper orthogonous. And this is important, okay? Due to the fact that anything in SL2C can be connected to the identity in SL2C through a continuous path within SL2C. But because this is broken up into 4 disjoint pieces, there are things which cannot be connected to the identity continuously inside a group, okay? Now, the argument is actually not as simple as that, but this is an essential feature which accounts for that fact, that the mapping, that the group homomorphism mapping, it's neither 1 to 1, being 2 to 1, nor onto, because there's a whole pieces in here which are not inside the image of that group homomorphism map. In other words, the group homomorphism takes SL2C only, because it's you know, takes SL2C only to this piece, this subgroup in here, okay, the proper orthogonous subgroup. And so, yeah.
What does SL2C look like?
What does it look like? We're going to come to that. It's S3, three-dimensional sphere, topologically, okay? One sphere is just a circle. 2 spheres, the ordinary 2 spherical surface that we know. S3 can be visualized as that part of, let's say you think of 4-dimensional Euclidean space, right? So there are 4 coordinates, x, let's say x1, x2, x3, x4. And you put in the requirement that the sum of the squares of these 4 coordinates add up to a fixed number. It's kind of like saying the radius of some sphere equal to a constant value, okay? We show that SL2C, because of the requirement of the S, the determinant being equal to +1. I'll show you that later, okay? But let me just, since you asked, topologically it is S3. It's like a 3-dimensional sphere embedded in 4-dimensional Euclidean space, okay? You can think of it that way. That helps you in thinking about it, but still it's hard to visualize what it looks like, because, you know, it's quite hard to visualize what are the 3-dimensional subspaces of 4-dimensional space, okay? Okay, now, then we started to talk about restricting this homomorphism to a subgroup of SL2C, which is SU2, okay? So then we can think of the restriction of phi to SU2. Anything in SU2 is definitely something in SL2C, okay? But not the converse, of course. So this maps SU2 to something inside of the Lorentz group. And I think we started this is roughly where we stopped last time, okay? And what we were able to show was that anything in SU2 under this homomorphism in here does not change the time unit vector, okay? It does not change the time unit vector, and therefore does not change anything which points solely along this vector, okay? Either. So it leaves the time axis alone. So you kind of guess that anything leaves the time axis alone only messes around with the spatial vectors which point along the 3-dimensional space. And in fact, we can prove that, in fact, it leaves 3-dimensional vectors the length of those vectors invariant. So it must be a rotation. It must be a pure rotation in three-dimensional space. So pure rotations in three-dimensional space is now a subgroup of the Lorentz group. And it's important to be able to think of it in this way. The Lorentz group is a generalized four-dimensional rotation in Minkowski space because it preserves the length of Minkowski vectors according to this metric in here. But then the three-dimensional rotations is a much more familiar kind of rotation that we are normally used to, namely just the ordinary rotations of three-dimensional vectors. Okay, and that of course also preserves the lengths of three-dimensional vectors according to the Euclidean metric. You see, if you don't worry about this one in here, this is just the Euclidean metric, right? Which is the identity, the Kronecker delta, like so. Okay. So we proved last time that anything in SU2 leaves the time axis alone. And the proof is very simple. I will not repeat it now. Now let us then look at what SU2 elements do to the orthogonal subspace, orthogonal to the time axis. And what is that? How is orthogonality defined? It means that the dot product between those vectors and the time axis is equal to 0. And how do you define dot products? You define it in terms of the metric, right? Because the metric defines the scalar product for you, okay? And so we introduced this subspace, which we're going to call the subspace which is orthogonal to the time axis, okay? Because E sub 0 is this one. First is the time component, so it's a unit vector along the time axis, so to speak, okay? Now, how do you define this? Of course, defined in terms of orthogonality is defined in terms of all those elements in Minkowski space which are perpendicular to the time axis. And the perpendicularity has to be defined in terms of the Lorentz, the Minkowski metric. So it has to be, so this is mu nu. So this one must be E sub 0 nu. Must be equal to 0, okay? Dot product between the time axis and these things are 0, which means that these things, all these things are orthogonal to the time axis. That defines the orthogonal subspace in M, which is orthogonal to the time axis, okay? Pretty much like, you know, if you're dealing with just three-dimensional space, and let's say this is a z-axis, so what's the orthogonal subspace to the z-axis? Just the xy plane. In other words, all vectors which are perpendicular to this one in here. But here it's a little simpler because the dot product is defined in terms of the Euclidean metric, okay? But here, you know, the dot product has to be defined in terms of the Minkowski metric in here, okay? And that's why a metric is something which is used to measure, actually, fundamentally, it's something which allows you to calculate dot products, scalar products. And once you know how to calculate scalar products, then you know how to calculate lengths of vectors, right? Because the length of a vector square is just a vector dotted with itself, so to speak. But now it's dotted with respect to the Minkowski metric rather than the Euclidean metric, okay? So you have to be careful about this. Now, let's work with something in the orthogonal subspace. Yeah?
Could you not equation? I mean, it's you're saying that the transpose of the time.
Not the transpose. This is a perpendicular. Transpose is a t. This is an upside down t. It's a perpendicular. Is that okay? So what is your question?
Never mind.
That's it, right? Okay. All right. It's not the transpose. It's an upside down t. So you look at this. It's the orthogonal subspace or the perpendicular subspace, okay, to the time axis, okay?
So is that space isomorphic to R3?
Yeah, it is R3.
Okay.
Yeah. Okay? It is R3. With that particular, with the Euclidean metric on how to measure. Because of this, you know, you take away this, then it's just the Euclidean metric. All right?
But say if it's perpendicular to one of the...
It's perpendicular to the time axis. It's perpendicular to the time axis because it dotted with the time axis is equal to 0. Any vector in this set which, when you dot it with the axis is equal to 0, must be in the orthogonal subspace to the time axis, right? And again, I ask you to think of this. Any vector on the xy plane, when dotted with the z-axis, is equal to 0, right? So it's the same thing. All right? If you really wanted to, you can do something like, say, this is the t-axis in here, and this is the xyz axis. You can't really think of it like that, but you can represent it like that by means of a picture like that, okay? So anything in this three-dimensional space is perpendicular to this one, okay? And again, the perpendicularity is defined in terms of this, is defined using the Minkowski metric in here, okay? All right, so then actually you can, with respect to this basis in here, then you can write something in some vector in here to have this form. It must have 0 time component, right? And then it would have whatever it would have in the other three directions, x1, x2, x3, like that. Okay. So you take any vector like that, you dot it with e sub 0, then automatically it would be equal to 0. Okay. But of course, the thing is that you don't have to express it with respect to the e basis like that. That's why we write a general thing in here. This e sub 0 itself can have components expressed with respect to some other basis in the four-dimensional Minkowski space also. This is one choice of basis in here, okay? Like that, all right? Okay, now, so let us take some vector in the orthogonal subspace, some vector like that, okay? So then you think of what happens to, under the map F, of these vectors in here. We know that already. Because any vector like that can be written as xi sigma I, sum over I going from 1 to 3, right? Right? Because the first one is equal to 0. So you don't have to worry about this one in here, okay? Sorry, you don't have to worry about this one in here, okay? Obviously, it is equal to that, okay? And so f of x, I'm sorry, I going from 1 to 3. There's no component along the first one, okay? Because this is 0 in here. So it's like the number 0 times this gives you 0, 0, 0, 0, okay? As a 4 vector. And so, so then if you take a vector in here, then f of this would be what? F of this would be xi f of ei, right? Summed over I. But f of ei is just sigma I going from 1 to 3. So this is equal to xi sigma I. So this is equal to xi sigma I, where sigma i's are given like that. Okay? Well, so this is fx. So if x is in the orthogonal subspace, so if x is in e sub 0 perpendicular, so if x is in the orthogonal subspace, then fx is equal to that. So this is a 2 by 2 Hermitian matrix, right? And so then you can tell what the homomorphism does to the particular sigma i's, okay? And now, so then we can use the homomorphism theorem. Let's say we take a G. If G is inside of SU2, if G is inside of SU2, you can tell what phi of G is by letting it act on X, where X is some vector in Minkowski space. According to that formula, it is equal to F inverse of G. F of X is xi sigma I, okay, and then G dagger. Well, but F inverse is a linear map, and so xi is just a number, so you can take it outside of that map, okay? So this is equal to xi f of inverse of G sigma I G dagger, like this, okay? So then the question is to find what is the inverse map of this 2 by 2 Hermitian matrix in here. You see the inverse map, going back to that diagram, takes some 2 by 2 Hermitian matrix back to some vector in the Minkowski space. Okay? And now, so let's, in order to see what vector it is, let's calculate the trace. Let's calculate the trace. You see now the trace, if you calculate the trace of this matrix, all right, what is that trace equal to? 2 times x0. If you calculate the trace of that matrix in general, it's 2 times x0, okay? But x0 is the time component of the Minkowski vector, okay? So if you can show that the trace of that matrix is equal to 0, that means there's no time component, okay? You show that the trace is equal to 0, then there's no time component for that particular 4 vector. And this is what we are trying to see now. What is the trace of this? What is the trace of this matrix in here? Okay. So if you take trace of sigma of G sigma I sigma plus. Now remember, I is only allowed to go from 1 to 2 to 3. We don't include the sigma sub 0 in here, okay? I only goes from 1 to 2 to 3, okay? So in other words, we're dealing with those matrices, those Pauli spin matrices. One of the familiar properties of the trace of a product is that trace AB is equal to trace BA. Trace of a product of 2 matrices in one order is equal to the trace of a product, the same product taken in the reverse order, okay? So if you take this to be A and this to be B, in the first grouping, the second one is B like so, okay? So that must be equal to trace G dagger G sigma I, okay? But remember, G is in SU2. U means unitary. Unitary means what? The inverse is equal to the Hermitian conjugate. The inverse is equal to the Hermitian conjugate. So therefore, G dagger must be equal to G inverse. Okay? And because of this unitarity requirement in here. So trace G inverse G sigma I. But G inverse G, of course, is what? It's the identity. Okay? And so this is just trace sigma I, where I goes from 1 to 2 to 3. Well, look at those 3. What are the traces of those? Each and every single one of those. 0 for all 3. Okay? So whether I is equal to 1 or 2 or 3, that must be equal to 0. Means the trace of this thing is equal to 0, means the time component is equal to 0. That means that the Lorentz, the Minkowski vector must lie in this guy in here. Must lie in the orthogonal subspace to the time axis. Okay? So in other words, you use the image under this homomorphism of something inside of SU2, the particular Lorentz transformation that results, not only does it not change the time axis, but it leaves the vector that it acts on within that same orthogonal subspace. And since it's required to preserve length anyway, it must be a rotation in three-dimensional subspace. Okay? And so we have come to this important fact that the restriction of SU2, lost it, that the restriction of phi to SU2 maps from SU2. Now, we have just shown that it stays in the same subspace and it preserves the length, but we haven't quite shown that it's actual rotation, so it can be something that involves a spatial inversion also. So this must be O3, okay? So it must be just O3, okay? SU2 gets mapped onto O3 under this group homomorphism. And O3, of course, is a subgroup of the full Lorentz group. O3 is a subgroup of the full Lorentz group because it's that subgroup which leaves the time axis alone. It doesn't do anything to the time axis. It only changes space vectors to space vectors in such a way that the lengths of the space vectors are invariant. So it must be either a pure rotation or a rotation combined with an inversion, okay? Or a pure inversion for that matter. Okay? And now let's draw another diagram. So So you have SL2C. There's a subgroup which is SU2. Okay. And the identity, of course, lies somewhere inside of SU2. Okay. And the homomorphism maps anything in SL2C to the Lorentz group. So this is a Lorentz group L4. Let's say the whole thing is Lorentz group L4. Okay. But the SU2 gets mapped by the homomorphism to O3, which is a subgroup of L4. And the mapping is 2 to 1, so that there are two elements. Take any element G, and then there's another element minus G, and both of them gets mapped to the same thing in O3 under phi, this group homomorphism in here. Okay? Now, actually later we haven't proved that it's a long involved proof, but according to what I have just told you 10 minutes ago, that the whole image of this SL2C is not the whole of L4. It is only the L plus up, okay? Actually, so this whole thing, the whole thing gets mapped to this part of it, which is L plus up. And these are the three parts of the L4 where this group homomorphism doesn't take you to, okay? Now that last statement is kind of hard to prove. It involves many different steps, but I'm just telling you this fact, okay, so that you have something you can keep in your mind, okay? What's happening in here in terms of the different objects, the mathematical objects that are involved. So this may be S plus down, this may be L plus, we have L plus up, L plus down, L minus up, L minus down like that. Okay? L plus up is a subgroup of the whole of L4, all right? But none of these are subgroups because none of them are groups, okay? Although they are the cosets of, including the 4 cosets, right? So the whole L4 divided by this thing in here gives you these 4 things as members of the quotient group. Okay? All right. Now let us take specific examples of some things in SL2C. And to do that, we're going to take a particular example of SU2. In fact, we're going to take 2 examples, 2 particular elements in types of elements in SU2 to see what that corresponds to, what kind of things in O3 it corresponds to. And then we're going to take something that is not in SU2 to see what that corresponds to over there in the proper orthogonal Lorentz group. We're going to see, we have seen already that this gets mapped to O3. So something which is not in here, we're going to see will get mapped to Lorentz boost, okay, which is definitely not something in O3. All right, you see what the structure of this whole thing is, okay? All right, so let's take the 2 examples in SU2 first. And try to find out through this homomorphism formula again what kind of element those get taken to in O3. All right. So the first one, we're going to take this thing in SU2. A very familiar kind of a matrix, diagonal matrix, okay, characterized by just a single parameter theta. And I claim that, of course, this is an SU2. Do you agree that this is an SU2? First of all, we have to check that the determinant is equal to +1, which obviously it is, okay? And then we have to check that it's unitary, which means we have to check that, what? That the inverse is equal to its Hermitian conjugate. Is it also clear pretty much that the inverse is equal to the Hermitian conjugate? What's the inverse of this thing in here? Can you read out what the inverse is? Okay. If you don't believe it, multiply these 2 matrices together, you'll see that you get the identity matrix. Okay? Now, do you also see that this is the Hermitian conjugate of this? It is, because you turn this guy rows to columns, columns to rows, and then take the complex conjugate, you get back this. First of all, you turned it into its transpose. Doesn't change anything because it's the identity. It's a diagonal matrix, right? And then you take the complex conjugate, it gives this one. Okay? So now we have shown that the inverse is equal to the Hermitian conjugate. Therefore, it is unitary matrix. It is 2 by 2, and it has special, and its determinant equal to +1. So therefore, it's a member of SU2. Okay? That's definitely something. Let's say something in SU2. So then we're going to try to see under that homomorphism what kind of Lorentz transformation that gets taken to by phi. Okay? And so we just plug in kind of. So let's calculate. Let's calculate this thing in here. Okay? So so to discover what kind of operator Lorentz transformation it is, we take any Lorentz vector, take any Minkowski vector, use F to act on that. So we get this guy in here, right? x0 plus x3, x0 minus x3, x1 minus ix2, x1 plus ix2. Take that particular G and sandwich this fx in between, G on one side and G Hermitian conjugate on the other side. So the G is e to the minus I theta 0, 0, e to the plus I theta. The Hermitian conjugate is e to the I theta 0, 0, e to the minus I theta. And I trust that you can do this matrix multiplication pretty easily, okay? And you'll discover This is the matrix that results. It's very interesting. The diagonal elements don't change. Check that first of all, okay? So what this tells you is it changes neither the zeroth component, the time component, nor the third spatial component. Okay? It obviously has to do something to the x1 and x2. But the thing it does to it can be written very succinctly like this. E to the minus I theta, x1 minus I x2, e to the plus 2I theta, x1 plus I x2. So now, can you see what it does to a Lorentz vector? Lorentz vector, originally the Lorentz vector was x0, x1, x2, x3. Okay? Gets changed by the image under phi of that particular G, gets changed to something that looks like this. I'm not going to write that down first, okay? But let me just write down the fact that neither these two gets changed, all right? So obviously, the x1 and x2 must change. Now, how does it get changed? If you look at the x1, x2 plane, all right, and take a look at that point on that plane, and you can express that as the complex number x1 plus ix2 if you think of x2 as the imaginary axis, right? So this one is x1 plus ix2 in here. If you look at the x1, x2 plane as the complex plane, with x1 being along the real axis and x2 being along the imaginary axis. Okay? So originally, this complex number is actually represented by this vector, if you want. Okay? Now you multiply this thing by e to the 2I theta. How does this complex number get changed? It's rotated in the positive direction by how much? 2 theta. Exactly. Thank you very much. E to the 2I theta, x1 plus ix2. Okay? This angle is 2I theta, rotated in, well, if theta is positive, it gets rotated in this direction, in the positive sense. Okay? So what does that tell you? It tells you that this represents a rotation about the third axis, so it changes only the x1 and x2 components, but not the x3 component. Okay, it's a rotation about the second axis, so it corresponds to R2. All right? So this thing in here maps to a rotation about the second axis, this particular one.
You mean the third axis?
Huh?
You mean
About the third axis, I'm sorry, about the third axis, right. So if you take g theta to be something like this, phi maps g theta to what? To, now it's a Lorentz transformation, rotation about the third axis by an angle 2 theta. If theta is here, the rotation angle is 2 theta in Minkowski space, or in the spatial subspace of Minkowski space. And of course, it's the same thing as this is equal to what? Because we have shown this particular 2-to-1 correspondence. Minus g theta also gets mapped to the same thing. Okay? Also because, also gets mapped to the same thing. Okay? There are two elements in here, g and minus g. If g turns out to be this one, both get mapped to rotation about the third axis by an angle 2 theta, like so. Okay? Now, let's take a look at another kind of SU2 matrix. So obviously, this is a very important kind of SU2 matrix because it represents a particular kind of rotation. All right? The next kind of important matrix I can show you before I do that. I mean, this is of course true, but I can show you explicitly why phi of minus g gives you the same thing, because now you just take this this for g theta. So minus g theta becomes what? Minus g theta becomes minus e to the minus I theta 0, 0 minus e to the e I theta. So that's minus g. Okay, but you can write this as what? The minus sign is e to the I. Huh?
You said that's minus g?
Minus g, yeah. So this is g minus g is this.
Okay, just 0 plus and
Where's a plus? Oh, that's, sorry, minus g. Okay. So minus 1 is what? Minus 1, a number minus 1 is e to the I pi. Okay. Minus 1 is e to the I pi. So I can write this as e to the minus I theta plus pi. You can write this e to the minus I pi also. Okay. E to the I theta plus pi. Okay. Now, you know that no matter what angle it is, it represents a rotation about the third axis by 2 times that angle. So what is 2 times that angle? 2 theta plus 2 pi. A rotation by 2 theta plus 2 pi is exactly the same as a rotation by 2 theta. So it's the same thing. So you can actually verify that explicitly. Okay. Although we have shown that in general that, you know, any g, not only the ones in SU2, any g anywhere in SL2C, it gets mapped to the same thing between g and minus g. It gets mapped to the same thing. Okay. Because SU2 is a subgroup, and obviously in this case in here, when g is like that, minus g is in SU2 also. Okay. All right. So we have now one important kind of element in here. All group elements of this form, there are many in here because theta can be anywhere between 0 and 2 pi. So in fact, there are infinitely many of these. Okay. But all of those corresponds to rotation about a third axis by some angle, which is twice as much as whatever this angle is. Okay? So that's a rotation about a third axis. Now you remember something called the Euler's theorem before? Euler's theorem says what? Any general rotation in 3-dimensional space can be represented as a product of 3 rotations, okay? About a second axis and about a third axis. Okay? In fact, do you remember what that Euler's theorem was? We talked about that several lectures ago. Lost that page. Seem to have. Oh. Any general rotation can be written in terms of the so-called Euler angles. Any general rotation can be written in terms of the Euler angles, rotation angles, about, let's see, 3 in the order 3, 2, 3, rotation about the third axis, rotation about the second axis, rotation about the third axis, phi, theta, and psi. These three are the 3 so-called Euler angles. Any rotation whatsoever about any axis, about any direction, can be written in terms of just rotations about a third axis and a second axis like that. Okay? So we have found all the SU2 matrices which corresponds to some R3. Okay? So all we have to do is to find another kind of SU2 matrix which corresponds to R2, rotation about a second axis. If we succeed in doing that, then we will have found all the SU2 matrices which corresponds to any rotation whatsoever because of the Euler's theorem. So let's do that. And so we have found R2 already, so let's now try to find R3. And it turns out that this particular matrix would do the job. This particular SU2 matrix would do the job. Let's see. Let me write this down first, and then we'll take a break. We call this other matrix G prime, and it depends on the parameter alpha. And this time it looks like this, cosine alpha. It's a real matrix now. Alpha is a real number, okay? And we have seen this matrix just about 3 million times up to now, okay? It's your matrix by the angle alpha on the about a third axis or something like that. But you know, it's a rotation on the plane, okay? But first of all, check that it is in fact a unitary matrix, okay? Why? First of all, the determinant is obviously 1. The determinant is cosine square alpha plus sine square alpha, so it's obviously 1. So it satisfies this designation S. Okay. Is it unitary? Yes, because its inverse happens to be its Hermitian conjugate. Now we know that this is an orthogonal matrix, right? Way back. So what's the inverse equal to? Transpose, right? But this is a real matrix. So the transpose is equal to its Hermitian conjugate. Okay? So that the inverse is in fact equal to its Hermitian conjugate. So it's a unitary matrix. So it's definitely something in SU2. And to find out what its effect is, we apply this homomorphism formula again. In other words, we put the fx, which is x0 plus x3, x0 minus x3, xi minus I x2, x1 plus I x2, slap in g on one, g prime on one side and g dagger on the other. So this is g f g prime fx g prime dagger is then going to be equal to cosine alpha minus sine alpha cosine alpha. The dagger is just equal to its transpose, so this is cosine alpha, or its inverse, sine alpha minus sine alpha, cosine alpha. And so you know what the action on a general Lorentz, a general Minkowski vector is by doing this multiplication of 3 2x2 matrices. Let's stop here for a few minutes, okay? We'll come back and pick up the story. Where does that G prime bring you to in the O3 in here? And I'm here to tell you that it represents a rotation about the second axis, okay? Now to show that it represents, it corresponds to rotation about the second axis, you have to do two things. Number one, you have to show that it doesn't change the second axis, okay? That means it's a rotation about the second axis. But then you have to find out also what the rotation angle is about the second axis. So first you apply this to E2, okay, which is the unit vector about the second axis. And then let's say you apply this to E3. And then see how much is that E3 rotated by. So if you have your E1, E2, E3 like that, okay, and you try to rotate about E2, then definitely both the E3 and E1 will get change, okay? If it's a rotation, you get something like this, okay? So this is a new E3 and this is a new E1 and so on. And we have to find out if this angle is alpha in here, how much is that angle? We're going to prove that angle is 2 alpha. So there's correspondence of 2 in there, okay? Let's see how that is done. How that's shown, rather. So first of all, let us apply this to E2, okay? If you apply this to E2 now, what is E2 in here? E2 is the unit vector about the second axis, so it's this thing in here, okay? So it means x0 is 0, x1 is 0, x2 is 1, and x3 is equal to 0, okay? So if you do this, well, x0 and x3 are both 0, so you have this, right? So x1 is equal to 0, and x2 is equal to 1, so you have minus I and plus I, like that in here. Okay? Whoa, that's sigma 2. You know that already. F maps E2 to sigma 2. But the thing is, if you actually do this, takes this in the middle of here, you'll see that it is again sigma 2. Prove this for any angle alpha. Okay? It's again sigma 2. Okay? So in other words, whatever rotation it is doesn't change the E2 axis. All right? Because if you use the inverse map, this thing, F inverse, this thing gets mapped back to E2. So the result of the image of this G prime, something in here acting on the E2 axis does not change the E2 axis. So it must represent a rotation about the E2 axis. Okay? Now, to find out how much the rotation angle is, you apply it to E3. Okay? So you apply this to E3. So what is E3? E3 is 0, 0, 0, 1. All right? That's E3. So you apply it to this unit vector in here. Okay? So in this case, you have x0 equal to 0, x1 equal to 0, x2 equals 0. So you have x0, 0, x3 is 1. So you have 1 minus 1, 0, 0, like that in here. Okay. Now, of course, this one is sigma 3. You know that, the spin flip operator. But if you multiply these together, you're going to discover that this time it is going to be equal to cosine 2 alpha, sine 2 alpha. Go home and do all these matrix multiplications, okay, which is actually part of these simple exercises in this in this chapter in here, okay? Now, it's very clear that under the map F inverse, this gets mapped to what? Which 4 vector does this get mapped to? It gets mapped to this 4 vector. 0, sine 2 alpha, 0, cosine 2 alpha in here, okay? Because this is supposed to be x0 plus x3. So x0 is 0 plus x3, which is cosine 2 alpha. This is supposed to be x0 minus x3, okay? So indeed, it is x0 minus x3, which is minus cosine 2 alpha. This one is supposed to be x1 minus ix2. Oh, x2 is equal to 0, so this number is real. So x1 is sine 2 alpha is 1x1 plus ix2, which is the same thing since x2 is equal to 0, sine 2 alpha. So, okay? Now, what is this vector in here? This vector is which vector? It has no component. So this vector is just, which has x, first component equal to sine 2 alpha, second component equal to cosine 2 alpha, okay?
third component equal to cosine 2 alpha. It's precisely this vector nu. Okay? So this one has first component, which is projection along the original E1 axis equal to cosine 2 alpha, sine 2 alpha rather, and then the component along the third axis equal to cosine 2 alpha. So we have shown explicitly that this represents a rotation which rotates about the E2 axis by an angle of 2 alpha. Okay? So we're done. We found all these are the general rotation axes about the second axis, and these are the pre-image under the homomorphism of rotations about the third axis. And because of the Euler's theorem, we are done, because now we know how to construct the SU2 matrices, which represent any kind of rotation, right? So for example, you can, going over to here, a general rotation can be written as, now this R3. This R3 is image under phi of G, what? Since the rotation angle, so this is, rotation angle is psi, so it must be G psi over 2. You see how it goes? Okay? And this must be rotation about the second axis. It's the of G prime theta over 2. Okay? And then finally, this one is phi of G. Whoops, sorry about the confusion in the symbols. This is a homomorphism, but this is the angle in here. I hope you don't get confused by this. Okay, this thing on the outside is a homomorphism symbol. This thing is the actual angle in the Euler angle. Okay. Now then, you know what 2 by 2 matrix, what SU2 matrix represents this general rotation, right? According to the homomorphism rule, the multiplication preservation rule, this must be equal to phi of what? G, phi over 2, G prime, theta over 2, G psi over 2. Okay? So you know each of those matrices, you know how to multiply them together, so you know what SU2 matrix represents some general rotation like that, written in terms of the Euler angles. Now, although this is not the only way that you can write that particular general rotation, okay? You write it like that if you choose the parameters to be the Euler angles, but there are many, many other ways to choose the 3 parameters of a general rotation also, okay? But up to now, we have shown that, of course, that the SU2 is a very special thing because it's inside of SL2C. It just gets mapped onto, the orthogonal transformations of 3-dimensional vectors. Now, finally, let's try to see something outside of SU2, but still inside of SL2C, okay? And see what that takes us to. And all we have to do is to look at a very simple matrix, 2 by 2 SL2C matrix. So let me now take out some space in here. Keep this general picture in mind. I'll leave this homomorphism formula in here. I'll keep this diagram in here.
Okay, let's look at a particular kind of SL2C matrix, which is characterized by some real number gamma. And we write the matrix like this. It's a real matrix, in fact. With gamma, and we call this G double prime, which is actually equal to its Hermitian conjugate, obviously, right? Because Hermitian conjugate is just that, because gamma is real. Hermitian conjugate is that you just change it to its transpose, but since it's diagonal, it's the same thing. Now, this is, of course, only a very special kind of SL2C. Okay? In general, there are complex numbers in SL2C. This one happens not to have any, because gamma is supposed to be a real number which is not equal to 0. Because you have this 1 over gamma in here. Okay? So now we will then take this one and try to apply that homomorphism formula and try to see, let's say this G prime prime is outside of, obviously it's not SU2, right? Because it's not unitary, right? Obviously it's not. Do you know why it's not unitary? It is not equal to its Hermitian conjugate, because its Hermitian conjugate is equal to itself, okay? And so the inverse of this is what? It's 1 over gamma here and gamma here, which is not equal to itself. So it's not unitary. But it is S. The determinant is equal to +1, okay? So definitely it's something that's outside of SU2, but still inside of SL2C. SL2C being any general 2x2 complex matrix which has determinant equal to +1. So this is a special SL2C matrix, okay? Because in general, you can have all diagonal elements and all complex numbers, but such that the determinant is equal to +1. So as we said before, it involves actually 3 real numbers. 4 complex numbers, sorry. Well, we'll talk about that later on, okay? It has the topological structure of an S3. Yeah, we'll talk about that later. But let's just look at this one first. So in order to discover what kind of Lorentz transformation that corresponds to, we know that, of course, it's not anything in here. So it has to be something outside. It has to be something inside of a proper orthogonal Lorentz group, which is not a spatial rotation or a spatial inversion and rotation combined. And so we again calculate this thing in here, right? We again calculate this thing in here using this particular G, which is G prime prime now, and use it to act on some general image of some Lorentz vector, which is then, again, this 2x2 matrix x0 plus x3, x0 minus x3, x1 minus ix2, x1 plus ix2. And so on this side, we have the G double prime, which is gamma 0, 0, 1 over gamma. On the other side, we have G dagger, but G dagger is the same as G itself, so we have the same matrix on this side. Like so, okay? So again, it is easy to calculate the product of these 3 matrices, and you'll find that after doing the matrix multiplication, you end up with this matrix. Gamma squared over here, x0 plus x3, x1 minus ix2, x1 plus ix2, 1 over gamma squared, x0 minus x3. Okay? So that's the result. Now, of course, you know again that what is this supposed to be equal to? This is some general, another Minkowski vector, which is different from this in here, right? But any Minkowski vector you can write in this form. So let us say that the components are the new Minkowski vectors x prime 0, x prime 1, x prime 2, x prime 3. That corresponds to this 2x2 Hermitian matrix in here. So this is x prime 0 plus x prime 3, x prime 1 plus
minus I x prime 2, x prime 1 minus plus I x prime 2, x prime 0 plus or minus x prime 3. Okay? So these two matrices must be equal to each other, which says that element for element are equal to each other. Now you take just this guy with this guy in here. Okay? These are complex numbers whose real parts are x prime, x1 plus I x2 must be equal to x1 prime, x prime 1. Sorry, plus I x prime 2. The inescapable conclusion is what? Is that x prime 1 is equal to x1 and x prime 2 is equal to x2. Okay? X prime 1 is equal to x1 and x prime 2 is equal to x2 means that this transformation doesn't mess with the 1 and 2 components. It only messes with the 0 and third component. Okay? It doesn't change the xy components in three-dimensional space. It only changes the time and the third spatial component. In other words, it mixes them together. You see, it mixes them together because, in fact, you can write down the equations, right? You can write down the transformation equations, which when you equate these, so you have x prime 0 plus x prime 3 must be equal to gamma squared, x0 plus x3. And then x prime 0 minus x prime 3 is equal to 1 over gamma squared, x0 minus x3. X prime 1 is equal to x1, x prime 2 is equal to x2. These are the transformation equations between the coordinates in Minkowski space brought about by that particular element in the Lorentz group, which is doing the transformation. Okay? Now, normally we would like to express each of the new coordinates in terms of the old ones. All right? Now, these two are done already. Okay? These two are done already. But these two are kind of coupled together, so we have to solve for x prime 0 and x prime 3 in terms of the x0 and x3. Okay? Doing that, you arrive at this simple result. It's just a simple algebra problem. You find solving those two simultaneous equations, solving for x prime 0 and x prime 3 in terms of x0 and x3. So you add and subtract those equations and so on, okay? And you find that very trivially, this is equal to 1/2 gamma squared plus 1 over gamma squared x sub 0. Now gamma is a constant, okay? Plus 1/2 gamma squared minus 1 over gamma squared x3. So you see, the new time component is a mixture of the old time component and one old space component, okay? And correspondingly, the new third space component is equal to this other linear combination of x0 and x3. With these factors reversed, it's gamma squared minus 1 over gamma squared. This one is gamma squared. So let me just write down the other two for completeness. X prime 2 is equal to x2 and x prime 3 is equal to x3. This doesn't quite look like anything you've seen in physics yet, but there's already an inkling of what we are about to get. This thing mixes the time component and one of the spatial components. It has to represent some kind of a Lorentz boost. Mixes time and space component. It has to represent some Lorentz boost. Which one is it? And judging from the fact that the x2 and x3 are not mixed, remain the same, this is going to be a Lorentz boost along the third direction. This is going to be a Lorentz boost along the third direction. Let's see explicitly how.
and you play a couple of simple games in here. Gamma is a real number, so let's introduce some positive value of this real number. And you write this as the exponential of another real number like that. You can always do that, okay? And so, now this assumes some interesting form in here. So gamma square is, now gamma square must be either, gamma is a real number, it can either be positive or negative. Gamma square must be positive, so it's a square of that absolute value of gamma, so it must be e to the 2 eta, okay? So it's e to the 2 eta. So this is e to the 2 eta, this is e to the minus 2 eta. So you have e to the 2 eta plus e to the minus 2 eta divided by 2. That gives you what? Hyperbolic cosine, a cosh of 2 eta. Okay? So making this identification in here, now x prime 0 is equal to cosh 2 eta x 0 plus, the other one is what? The other one must be a sinh, okay? It's a sinh, as they say. Okay? E to the 2 eta minus e to the 2 eta divided by 2 is a sinh of 2 eta times x3. And this one is reversed. 3 is equal to sinh of 2 eta x0 plus cosh of 2 eta x3. I won't bother to write down the other two now because they are not changed. Okay. One last now. No, before I write down. Well, actually, let me do this. Cosh and sinh has to satisfy the property that the square of the cosh minus the square of the sinh of whatever is equal to 1. Okay, just like the sine square plus cosine square is equal to 1. So the cosh square minus sinh square is equal to 1. So I'm going to change to yet another parameter, so to speak. This time I'm going to write cosh. And this time the cosh can vary a whole lot, okay? And it's a positive, but can vary from 1 to infinity, is that right? The cosh, right? And so, so I'm going to define cosh 2 theta to be equal to 1 over 1 minus v square over c square. But v is supposed to be less than or equal to c. And now we bring it into contact with physics, okay? And so if cosh is equal to this, then the sinh must be equal to minus v of c divided by 1 minus v square over c square, like that. Okay? And so I will now have this transformation, x prime 0, which is the new time coordinate, is equal to, now there's a factor which is 1 over 1 minus v square over c square. And then this would be x0 minus v over c, right? Minus v over c x3. And then x prime 3 is equal to 1 over 1 minus v square over c square. Sinh. So sinh was what? Minus v over c. x0 plus x3. Cosh is 1 over this. Okay? So now that looks like the ordinary Lorentz transformations that we are used to in physics 234. Okay?
And because of the fact that that eta, you see, the way it's defined in here, eta can lie anywhere between minus infinity to infinity. So, so eta is essentially a parameter within this SL2C in here. So this makes SL2C and also the Lorentz group what is called a non-compact group. Okay, unlike the rotation group where all the parameters have finite ranges, you know, like between 0 and 2 pi and so on and so forth. Okay. And of course that the phi of G double prime gamma is the particular Lorentz transformation we labeled that as A mu nu, which is characterized by eta now. This is a 4x4 matrix. And the 4x4 matrix is then cosh 2 eta 0 0 sinh 2 eta 0 1 0 0 0 0 1 0 sinh 2 eta 0 0 cosh 2 eta. You can calculate this, that the determinant is equal to +1, okay? And this element, this 0 0 element, is indeed larger than or equal to 1, so it belongs in here. It's a proper orthogonal subgroup. Okay. Now we still have to prove that, to prove more rigorously that the whole image is the whole thing in here. We've proven that, you know, that some special thing in here, the gamma, the G prime of, oh, I erased that matrix, right? This particular thing, G gamma, this guy in here, where gamma is a real number, non-zero real number. This is something in here, and we have proved that this thing actually takes you to that particular Lorentz boost, which is a boost along the third axis, okay? But we haven't quite shown you that other kinds of boosts arise from other things in here. And in fact, the whole of the image in here is all of the things in here. All boosts and all rotations, so to speak. All boosts in any direction whatsoever, okay? And this is a long proof. I'm not sure if I want to go through that. It's given in your notes. I'm not sure if I want to go through that in some detail, but let me just mention the key results in here that you need to make use of in order to establish that proof, okay? First of all, you have to somehow show that none of these things are in the image of this homomorphism map, okay? And then you have to prove that all kinds of boosts arise from, in other words, a boost along any direction whatsoever arrives from some SL2C in here, okay? Now let's go back to the physics a little bit more. What is meant by a Lorentz boost, okay? The original physical consideration is this. This is special relativistic physics, right? Where we do our experiments in three-dimensional space in here, so we have a three-dimensional frame. Let's say it's a what in classical mechanics is known as an inertial frame, and there's a second frame that's traveling with respect to us at some speed which is less than the speed of light, and that speed is constant, that velocity is constant, let's say, and obviously that's going to be an inertial frame also. Any frame that is traveling at a constant speed relative to an inertial frame is also an inertial frame, because in both of those frames, Newton's laws remain unchanged. There are no non-inertial forces coming in, so to speak, okay? So physically, the situation is this. You have, let's say here we have chosen one inertial frame, x, y, z. Here's a rocket going along in this direction at some constant speed, and this rocket is boosting or being boosted with respect to this one. with some constant velocity v, okay? And so the coordinates here would be x prime, y prime, z prime. So let's say there's an observer in here, an observer at rest with respect to the other frame, and both of them observe some physical event, okay? Now, what is a physical event? A physical event is just some point in Minkowski space, all right? And so Minkowski space, you see in textbooks, is represented like that. This represents a three spatial axis. This represents the time axis in here. An event is just a point here, where you are and what time you're at, okay? And so a physical process is represented by a world line. It's in the physics language, so to speak, okay? So the world line, you may have something that starts off in here, you know, some world line in here like that, okay? World line says where the thing is at what particular time with respect to some frame. Now each point in this world line has 4 coordinates, right? It has a time coordinate and it has 3 spatial coordinates. But those coordinates will be different with respect to these 2 different frames, okay? A guy carries a clock here, tick-tock, and this guy carries his clock there, tick-tock. This clock is at rest with respect to this guy. This clock is at rest with respect to this guy. So this guy measures something happening at a particular point in space and at a particular time represented by the coordinates x0, x1, x2, x3. This guy measures the same event and times it using his clock, which gives 4 coordinates, x prime 0, x prime 1, x prime 2, x prime 3. According to this theory of special relativity, those coordinates are related to each other through Lorentz transformations. And if this frame is boosted along the 3rd axis, let's say this rocket is moving along this direction, okay? Then the transformations will be given by that set of equations that we have just written down. All right? Now then the idea is, so this is the meaning of that transformation, right? You have to understand what the physical meaning is. It's a guy carrying a clock and that guy carrying his clock. In Newtonian physics, you can synchronize those 2 clocks at one time and then thereafter they would be synchronized, okay? So in Newtonian physics, time is not a coordinate. It's a parameter. It's a parameter. But in relativistic physics, time is a coordinate also. So that if they're synchronized at one place and at one time, they will no longer be synchronized if one of them is moving with a uniform velocity relative to the other one. This is relativistic physics, okay? And the laws of relativistic physics tell you how those times and space components are related to each other, and they are related to each other through the Lorentz transformations, okay? And so then the next question would be, well, if indeed this guy is boosted along the 3rd axis, then the transformation equations would be like that. But what if they're boosted along any other direction in physical space, okay? Then what would those transformation equations look like? Do you know how to work that out? Okay, here's let's see.
Google it, right?
Yeah, that's one way. Go home and try to Google it, okay? see which one of you can come up with the result the fastest, okay? But let me tell you the result, okay? It's in fact, the result is interesting to prove. I'm not going to prove it, okay? If I can find it. Let's see. Yes.
Okay, this result is rather useful. It's very useful. And any L4, any L4 whatsoever, any proper, anything in L plus up, anything in L plus up, okay? Anything in L plus up, it's kind of like a slight generalization of the Euler's theorem in three-dimensional rotations. In that case, any three-dimensional rotation can be written as a product of three rotations, one of them around the third axis and, two of them around the third axis and one of them around the second axis. So this theorem says that any lambda in L plus up can be written like this. R B3 R prime. Well, R prime and R are two separate rotations, actual three-dimensional rotations. And B3 is a boost along the third direction, okay? So then it's a matter of finding the rotations which would kind of rotate you from the third axis to this particular direction that you want the boost to be along. And then, then you can find that particular, whatever that lambda is. Now that lambda may be not just a pure rotation, but maybe a pure rotation and times a rotation or whatever, okay? So it's a much more general thing. But whatever it is, it can be written as this thing in here. Well, R and R prime are two, in general, different rotations in three dimensions. And now B3 is a 4x4 axis, so you can write an R and R prime as a 4x4 axis also, but obviously a 4x4 axis which doesn't change the time, a 4x4 matrix which doesn't change the time component, okay? So you have lambda 0, 0 equal to 1. Along the first row, it's all zeros, and along the first column, it's all zeros. And the rest of it is just the actual rotation matrix, all right? So you can think of this as a general Euler's theorem, if you will, which allows you to write any proper Lorentz transformation in terms of a boost along the third direction and two actual rotations. I think this would be a good place to stop here. Okay. We've gone through quite a bit today, so it may be helpful if you go home and try to follow the lecture notes that I've given you. Okay. Oh, also I promised you I would give you the solutions to the problems 9 and 10 at least for the exam, but I haven't finished writing it down yet, so I'll give that to you a little bit later. Yeah.
What chapters are the second midterm part? There's this one.
Well, obviously it will be this one, and then have we tested the one on SO4 last time? We have.
Yes.
Yeah. So obviously it will contain this one, maybe plus a little bit more. Yeah. When is that going to be? Yes. It's probably going to be the beginning of the 9th week. Probably on a Monday of the 9th week. Okay. It will be similar to the first midterm. In other words, mostly kind of conceptual and definitional and so on, with a couple of small calculations. Yeah.
This is me curious because I'm taking GR right now, but all of this is for the calculus. Right?
All of this is for flat space.
So
Yes. The Lorentz group is rotations in flat space.
how would it look like in a general case?
General case is much more general class of transformations. It's called general coordinate transformations. Not just things related by the Lorentz transformation, but any general coordinate transformation, where x prime 0, x prime 1, x prime 2, x prime 3 are related in any general nonlinear way to x0, x1, x2, x3. Okay?